So we subtract this and this into 0. The b minus a k is identical to 0, which is saying, which is if and only if, which implies, if and only if, or now implies p divides b minus a, or p divides k, which is a contradiction. And the reason why is because b minus a and k are both less than p, and greater than 0. So therefore, therefore these things, these two, have to be different. So we must have p of them. So the words these indices, let me circle these. These indices must all be distinct. Because if they were the same, then b minus a times k is identical to 0. And now apply p divides b minus a or p divides k. But that's impossible because b minus a is greater than 0 and less than p. And by fundamental theorem arithmetic, impossible. Good. So because though these are actually, since we have p different ones, it actually is a permutation of 1 up to p in a different order, and because they're p different ones, x1 up to xk plus 1 up to xp minus 1 times k plus 1 are all equal with p different indices. Okay. And because we know x1 times x, and now this is the same, x1 times x2 times x3 times x to the p is equal to e. And this is really just saying x1, because this all of them are equal to some x, is saying x to the p is equal to e. Okay. And because, and we already made the assumption that this guy was not e. I'm trying to think where. We threw it out earlier. We threw it out when we considered this class separate from e. Yeah, we pulled it up there. Because they were not all p minus. Assuming that one e, then we used proof by contradiction to say that one of them was one of those sets that did not include e must have had one that was not of order p. We had a contradiction. So therefore, for this guy, x is not equal to e. There you go. Okay, this was not an easy proof, Cauchy's theorem. And yeah, thank you. Well, that was not an easy proof. So now, this property is that we now know, given a group of some order, it must have elements that have order of its prime divisors. Okay, let me look at this in the proof again. I think there's a better one in Dumb Foot, but this one, it gets a little bit sketchy around the second part, everything is good. But then, even, actually that makes sense. Yeah, this is definitely something. Okay. So, alright, let me try to summarize the proof. Consider all the set of strings. Yeah. No, I had it down, but it's a fast proof. I read it through and it was right. But it's just when I think about it. I wish there was an easy picture I could paint, but Cauchy's theorem is that so what you did is you consider all the set of p strings such that when you multiply every element in the string, it equals to e. And you prove that this set, it has to have order that is divisible by p. Okay. You define the equivalence relation. You argue because of the equivalence relation of things that are equivalent if they're both cyclic to each other. If two strings are cyclic to each other. And because you argue that, you can argue using proof by contradiction, simple argument, and using the fact that P divides the order of the set of all of these special strings. We do a partition on the set. P, one of those Kunz classes that does not contain all E must contain a size smaller than P. And so we can say, because it contains size smaller than P, things must repeat. Therefore, it has to repeat with some cycle K. But then you use the fact that you then use number theory and the divisibility rules to argue that they must go, that each of these things, even though they repeat elements, each of these things are equal by cycle K. By the nature of the P being prime, then all these indices must be different. Even though, and because they're different, all P of them are different. P of them different. Therefore, the remaining, therefore, even though the things are equal, then we have P different indices with X of that index being equal. And from there, because it's still P, we must have, and it's not P, it has order P. Okay, I'm happy with this group. The book maybe did not even, pretty lousy in my opinion. It's not a lot, Domenico covered it better. But that's because they only teach it after they teach actions, orbits, and stabilizer. Okay. Anyways, you can see some good exercises with this. Yeah. So that will be the sums for this week. Next week we're going to talk about conjugacy classes. Now those are much simpler than proving Cauchy's theorem. Anyways, thank you very much. Math Ninja, out!